Hi, everyone. My name is Matthew. Hi, everyone. My name is Matthew Rocklin. I'm an open source software developer in the SciPy ecosystem. I recently joined Nvidia, but I mostly work on Dask, along with lots of folks here. I'm talking about some of the work that we've been sort of playing with, both with Dask and refactoring system to work well with parallel computing, and then also now with GPUs, and how sort of lessons from those two experiences we can maybe propagate out to sort of open up the ecosystem generally towards new hardware, new domains, et cetera, and sort of the strategic reasons why we might consider that. I'm a little bit injured, so I'm actually going to sit down for most of the presentation. Hope you don't mind. So, two main messages. GPUs are neat, and we should think about standards. Talk to me sort of split along those two pieces. For the GPUs are neat part, I'm going to be wearing my Nvidia hat. For the other part, I'm wearing my sort of open source hat. I actually tried to get an actual Nvidia hat for this presentation. That didn't work out. So GPUs are neat. First, let's just switch to an example. I'm on a DGX machine. This is a very expensive machine, but you can get a cheaper version if you want. I'm not using the whole cost. So, yeah, we got in there. Working on it. Great. So let's make a NumPy array. Is that good? Great, thank you. And I might time some operation. So I'll do some element-wise operations. I might then do some slicing. And then do some aggregation at the end. That's going to run some time. We can all write code like this. This is actually calling C or Python or Fortran code that we probably couldn't write. Python is really good at giving us an accessible interface to a language that most of us can't write in. We can do the same thing with CUDA. So I cannot write CUDA. I wrote like a small amount. I work for Nvidia. Nvidia makes GPUs. Most GPUs are written in CUDA. GPU programs are written in CUDA. I don't know how to do that. But I know how to use NumPy. And so if you stay for the next talk, you'll learn about CuPy, which looks a lot like NumPy, but it runs on the GPU. This is allocating an array on the GPU, and I can do the exact same operations. Actually, don't even need to make these changes, but I am, just to be pedantic. And I'm going to have to actually call float here at the end, because CuPy is a little bit magical. This is going to run, same code, same result, just order of magnitude faster. So we all know how to use GPUs now. Not that you should, but it's something you could choose to do. There's a different performance profile, there's a different cost profile. It's going to be good at some things, not good at others. But we can now play and experiment, and that's new. So a colleague of mine, Peter Enshev, compared a Xeon processor versus a Tesla V100. It's a pretty expensive CPU compared to like a very expensive GPU, but he's getting sort of 10 to 100 times speed ups, depending on the operation. Actually, when we did this at first, the SVD computation was slower on the GPU. Then we sort of upgraded the CUDA version, and everything was faster again. The sum was also slower, but it turns out in CuPy they had a bad implementation. Someone had already been working on it. But generally, there's like a different plot in our minds. We need to learn more about these different performance profiles and how they might affect our work. The point of this talk, though, is that you can do that. You have the knowledge to use GPUs and play around by switching out imports and switching out hardware, and that's new. Another fun example. No, too big. So again, I usually work on Dask. And here's a Dask array. So this Dask array is composed of lots of little NumPy arrays. This is a really tall and skinny array. We're going to compute an SVD. So this SVD algorithm is quite complex. It was written by a gentleman named Mariano Tepper, who was a postdoc in math at Duke and presumably is doing something else now. This is taking a while not to compute. It's actually just plotting out the graph of the computation for us. It looks like this. So you can't see that because it's really small, but all those little dots are little NumPy computations like QR decompositions or matrix multiplies or much smaller SVDs. If you do all of those things, then you'll end up computing the full SVD of this big array. Let's go ahead and run that. I've explained, at every talk that I've given in the last like 5 years, I've explained the Dask task graph. And in this talk, I'm not going to do that. I'm going to assume that you guys know what that is. So each of these is using 10 threads each. There's 80 logical cores on this machine. It's a dual socket CPU system. And it's doing a bunch of QR decompositions. Eventually, it'll do some other work, and then it'll sort of do some communication, then it'll finish up with the SVD. We're just going to wait for a minute and just sort of feel that performance. This is really awkward for me, but
feels awesome.
Just wait. Just wait. This is like a $100,000 machine, not for the CPUs.
Persist while you're waiting?
Sorry?
Can you explain persist while you're waiting?
Why is it called persist?
No, I'm not going to do that. Go see a Dask doc. What I'm going to do is I'm going to switch out NumPy for CuPy. Right, so this Dask array is a Dask array of NumPy arrays. So Dask array usually has lots of little chunks of NumPy arrays. Now those little chunks aren't going to be NumPy, they're going to be CuPy instead. And you might think, oh, that's going to require a ton of rewriting. And it's not. Well, I mean, it did, but internally instead of NumPy. Thank you, NumPy developers. So because of Maddie's work and lots of other people's work, Peter Ensheb did a lot of this work too, I had to make that change. So I'm saying, hey, Dask, make a random array, but use CuPy to make the random arrays. And the rest of Dask is gonna work just fine. So we're going to, again, call the exact same Dask linalg svd command. I'm not going to call this because that takes a while just to plot the graph. And we're going to call persist again. And so these chunks that used to take 3 seconds now take 300 milliseconds. And I can compute this whole thing much more quickly. It is actually a bit slower in communication, so the red at the end is communication. So this is actually something we're working on. We're improving network speeds. After we've made the computation 10 times faster, turns out communication ends up being our bottleneck. The point here is we had a complex algorithm represented by this image. We were able to use that exact same code. You don't have to rewrite that code. You don't have to like unearth Mariano, the author of that code, to write it for GPUs. Everything just worked on CuPy. So that's the magic. That's the neat trick. And you can do this with lots of other things, not just with Dask. We'll make this work with Xarray and other tools that use the NumPy API as well. Anything that uses just the NumPy API should eventually end up being able to use GPUs or other things. You can make other NumPy-like libraries, and that's maybe the focus of the rest of the talk. So we've seen this. It's kind of neat just to do that, and everything just works, including that really scary graph in the bottom. GPUs are good for other things too. So those of us who work on Dask within Nvidia are part of the larger Rapids group. Rapids tries to build a lot of the SciPy libraries, like NumPy, Pandas, scikit-learn, but on GPUs. So here's Pandas reading a 2 gigabyte CSV file. It takes around half a minute. Pandas read CSV runs at about 50 megabytes per second. And the same code, effectively, but with cuDF, which is the Rapids Pandas library, takes around 2 seconds. Rapids cuDF runs at around a gigabyte per second. Which means that you can read a CSV file about as fast as you can read a Parquet file, which is fast. And this is odd if you know GPUs. When I learned GPUs, I thought, oh, they're good for dense matrix multiplies. They're good for deep learning. They're good for image processing. They're good for graphics. Not so good for parsing text. Oddly, good for parsing text. But so also note the API is the same. cuDF implements a decent subset of the Pandas API faithfully. If you know how to use Pandas, you know how to use Pandas on a GPU. That's not entirely true. There are like lots of little holes, there's lots of little issues, you'll have some frustration, but mostly things work great. Same is true with Dask data frame, right? We don't implement everything. We implement most things, and there are bugs. But yeah. UMAP. So UMAP is a library that is awesome at the moment. It's written in Numba on the CPU. There's a GPU UMAP that runs quite a bit faster. Same keyword arguments, drops into scikit-learn pipelines, looks just the same. So again, you know how to use GPUs if you want to. So we don't have to write CUDA to use a GPU. Libraries like Rapids, CuPy, which is the next talk, and Numba, which is the talk after that, provide similar APIs around GPUs. So Nvidia has made it very easy for you to use GPUs so that you buy more of them. So again, 2 parts of the talk. GPUs are neat. That's what we just seen. And then we need to think about standards. So that's what we're going to talk about next. So I'm taking off my Nvidia hat for a moment, put on my destroy all the evil corporations hat. So think about standards. Whoops. Whoa. Okay. So the SciPy ecosystem is expanding. We are wildly successful. Right? We used to be a bunch of graduate students who sort of coded in our off time, making some fun libraries. Now we're at the core of Fortune 500 companies, at the core of lots of large research institutions. We're at the core of scary government institutions. We're also supporting millions of researchers, and that's great. There's lots of new faces. Hi, everyone who's your first time here. Looking forward to meeting you. Lots of new domains, things that I didn't know SciPy could be used for. Genomics, cybersecurity, genomics, text processing, and lots of other things. And lots of new technologies too, right? Multi-core CPUs and clusters, that's sort of what I've thought about for the last few years with Dask and others as well. New technologies like GPUs, those are sort of coming in. That's where the last part of the talk was about. TPUs, Google has hardware. Lots of companies are making their own hardware. ARM chips are getting quite exciting. So there's more stuff that's going to come into our ecosystem, whether we like it or not. And we're going to have to sort of figure out how to deal with it. And a lot of those people who are putting that infrastructure into our system are large companies, or they're cool startups, or they are philanthropic organizations. And we should welcome them and make space for them, because they're going to be here. And that's maybe what the rest of the talk is going to be about. So it is great, but also scary. It is scary because the ecosystem has grown up to work well together. And putting a new piece, sort of dropping TensorFlow into that system is going to be hard and not cause too much craziness. So we need to think a little bit intentionally about how we add new pieces to this ecosystem. And this requires some care. Otherwise, we might fracture the ecosystem. So some history. A long time ago, before NumPy, there were 2 libraries called NumArray and Numeric that sort of served NumPy's purpose. And you sort of were on one side or on the other side. And that fractured things. If we were to build libraries on top of that, we had to choose which camp we were in. And that's tricky. Eventually, NumPy came around, it united the ecosystem, which resulted in this sort of golden age where everything worked well together. I could read from an HDF5 file, I could compute on it, I could plot it with matplotlib. Those libraries didn't have to know about each other. Matplotlib and HDF5 didn't have to sort of have hooks to each other to work well. Everything worked on NumPy. Pandas came around, and that was great in lots of ways. But there was some frustration because NumPy wasn't able to move fast enough, like date times. Pandas needs good date times, and the NumPy developer community or the NumPy project wasn't able to adopt date times in a way that was acceptable to Pandas. And so there was some split, and that caused some frustration. So there's a little bit of a fracture that we experienced, and that was painful for a lot of us. We didn't get a lot of attention, and that same fracturing is happening again. If you look at n-dimensional array libraries accessible in Python, it's not just NumArray and Numeric, there are 10 different array libraries, and that's concerning. So we're back in the 90s, but with a bunch more pressure. Right? If we don't do anything, things are going to go sort of haywire, I claim. So in order to facilitate growth, we need to organize a bit. We do this carefully and with intent, but also quite quickly. And the way in which we're doing that, I think, is through adding new standards. So I would like to highlight a few successful standards, just to show people what those look like and how we can build more and why they're useful. So the iter protocol in Python allows any object, including an object I write, to work inside of a for loop. And that's neat. I feel like very much a first-class citizen when I do that. It's very cool to say like for I in my object and have everything just work well. The NumPy Array protocol, if you implement that on your class, you can look NumPy-like. And that's why how things like matplotlib work. They look for that protocol, and they use that to render your plot. So this works with NumPy, because matplotlib knows NumPy, but it also works with pandas, even if matplotlib doesn't know pandas. That's because, again, the pandas series object implements the array protocol. So that protocol is really important, and that came about from lots of conversation and discussion and consensus, and that process is really important. We can do lots of things. We can pandas in an HDF5 file, Dask in an HDF5 file. We can put an HDF5 file into a ZAR file, go back the other way. It's fun. So standards lets us mix and match technologies, and that's really valuable. We can sort of match these things up and be really creative. Right? So the NumPy, Pandas, scikit-learn developers are actually not that creative. No offense, guys. The broader community is far more creative, and they can come up with lots of new fun things. And these protocols allow that creativity to happen outside of the core development teams. So another good example, fit predict out of scikit-learn. So if you implement these and a few other things, you can use scikit-learn objects inside of things like pipelines, or you can use other objects like UMAP, or again, like Rapids UMAP. So Nvidia was able to produce one piece, a fast algorithm that could plunk into a lot of existing code because of this protocol. So that protocol really allows lots of people to interact well. The Jupyter Notebook standard was designed originally for notebooks. But once that standard exists, other companies can show up and add value. They render on GitHub nicely. If there were 3 or 4 different notebook standards, GitHub wouldn't spend the effort to have our notebooks render nicely. But because we're all one target, it's very easy to do. Netflix has a ton of work. If you've never seen a Netflix Jupyter talk, they're great. And we're benefiting from that work. Things like Papermill, et cetera, those are coming back to us. This is a great example of a standard that exists and a company that engages with that standard, and the open source community benefits. We sort of set out the rules, they engaged with those rules, and everyone benefited well from it. Voila, it's a nice new thing that exists that can benefit again from all these things. Recently, we've been thinking about computation. So there's the array function protocol. This is quite new. This is what allows any NumPy function, like the SVD function, for example, to operate not just on NumPy arrays, but on Dask arrays, or CuPy arrays, or sparse arrays. It's up to the library now to say, I can handle that function. And so code that was written with that NumPy code can now work on all these other things. And that's recent work. I'm very happy NumPy developers did that. It's caused a lot of activity outside of NumPy. We're all very excited. Including libraries like Xarray, right? So this doesn't just work for NumPy itself, but any library that's built on top of NumPy can now use any of these other implementations of NumPy. So this standard creates this sort of boundary interface that allows for all this creativity. So this is great. Standards level the playing field and allows new technology to enter. So in Nvidia, we wanted GPU arrays to be easy to use. We sort of pushed on these standards, now they're there. Now some other much smaller company can come in and can say, hey, I've got my own NumPy-like array. I want to play too. And it's much easier for anyone else to come in and disrupt that space. So that's the approach that we're taking at Nvidia, and it's, I think, a good one. We're very much opening the doors for other people to engage. So for example, there's a sort of antiquated CLPy array, which works on OpenCL. I haven't tried it, but someone could. And it'd be fun to try that out. So this also allows users to play around with new technologies. They can play very easily. You all can try GPUs, which is great, or other things. So you can just throw a sparse array inside of Dask and see what happens. So, or throw GPU data frames inside of Dask and see what happens. We don't have to sort of plan this ahead of time. So Dask arrays are usually NumPy arrays. They could also be CuPy arrays or sparse arrays. There's Dask data frames, which can have Pandas data frames or GPU data frames, or maybe in the future Arrow data frames, or your own data frame. You might decide that you want to re-implement Pandas, and these standards allow you to now engage with the rest of the ecosystem. And this is great because there are much fewer fun projects to do. 5 or 6 years ago, you could have made Pandas. You could have made the way to do optimization in Python. And now there aren't. There's like a huge pile of issues in Pandas that you're welcome to handle. It's actually much less fun to be a young developer, I think, today. But this sort of standards create lots of new spaces for those people to add something and have it integrate nicely into the ecosystem. I think we actually need that. I think the core developers are aging quite a bit. They're getting kids, they're getting real jobs. We need more PhDs, young blood that we can suck out of. And they're not going to just write issues, right? They need something fun. As an example, so Pandas extension arrays, another excellent example of a cool protocol. So internally, Pandas has lots of things that look kind of like NumPy, but not quite. Date times, categoricals, et cetera. They sort of formalized this. They had a lot of code. Internally, they refactored it and said, hey, this is what a NumPy-like array looks like for our code base. And what that means is that both the internal code is nicer, but also external libraries can implement things like IP arrays or MAC addresses. as a fully native pandas series type. They don't have to get the buy-in from like the core pandas community, which is intense if you're inside of it. They can just write that on their own, publish it on PyPI. And yet through these protocols, through these standards, they are native. They're as native as if they were inside of pandas. And that's really cool, right? Small companies can engage, they can add value. They don't have to fork out pandas, they don't have to make some other thing. GeoPandas used to be a separate project, and now maybe it's coming into sort of more mainline pandas because it can integrate more natively. You can imagine doing something else. What are some other types you might care about? Maybe you care about quaternions or something. You could build that very easily, and you could be, again, pandas native. So if you're a graduate student, this is like a fun place to engage. And as a result, it'll work with things like DAS data frame, right? Make it work for pandas, because of the ecosystem thing, all these standards, things built on top of pandas will also just work, mostly. So, the core projects need to define clear contracts, and we're doing that. And that enables external growth in lots of ways. It invites people to play an ecosystem in a well-defined way, in a well-defined manner that I think is good to define the rules for. That's also how we get to direct the growth, right? I claim that if we had had NEP18, the array function protocol, prior to TensorFlow or PyTorch being around, they would have followed that protocol. And then we could have used NumPy, Pandas, PyTorch, TensorFlow much more consistently without having to sort of split. And so we need to sort of, that's also, we currently have this sort of window now to direct what happens with these standards. We have a lot of power right now. That power is leaking out. We should like consolidate with standards. So in summary, GPUs are neat. I encourage you to play. It's fun. I'm actually quite curious to see not how much we can accelerate deep learning, but how much we can accelerate genomics or curing cancer. There's 100x speed up out there if we're careful with it. How does that change how we think about what problems are possible? I know I like have the Nvidia hat on again, but I'm wearing both hats. Play around, it's fun, it's easy. And the revolution is coming, so let's make a plan. So if you are a user, I encourage you to experiment with new technologies. Play around with GPUs, play around with TPUs, play around with ARM, and write about it, share about it. I have no idea what's going to be fast or slow. Right? There's all these new things that are coming out. We have all this intuition around CPUs and around NumPy and around Pandas. That intuition is now broken, and we need to sort of rebuild that intuition, and that's, I think, where we all come in. Developers, I would encourage you to build on standards and not closed systems. Maybe you want to use Amazon Lambda, for example, for serverless functions. Fantastic idea, but if you build on that, you then can't go over to Google. Maybe we can find some standard that we can sort of apply to both, like the concurrent futures interface, for example, or JobLib. Those are maybe standards we could build on, and then sort of have a small hook to the services. Core maintainers, I'd ask that you think about building extension points and understand that there is some time pressure. Just be careful, but also fast. So that's it. I'm going to open for questions, but before that, I'm going to take an SVD of an 8 terabyte array. So this is using NEP8, NEP18, just checking that it's active. This actually comes out of Alastair Miles. Are you in the room somewhere? Hey, hi, Alastair. Alastair's a geneticist, a genomicist, what should you guys say? He has an array that's like 100,000 mosquitoes by like a few million gene things. And he wants to do an SVD in low memory. We actually don't have 8 terabytes of RAM or even GPU RAM. And we're just going to get this going. And we're going to set up for questions. Great. So that's going to run. It's going to hypnotize you, so the questions are easier. And that's it. And so we have a microphone. I will pass it around and people can pass it.
You said core developers should build extension points. Can you elaborate on that a bit?
Yeah, so I think, for example, the Pandas array interface is a good example. The Pandas core development team decided, hey, we have all these requests coming in for all these weird kind of data types we don't want to support. Let's make a standard interface, and then people can, that's an extension point, that standard interface. So other people can hook into that and that'll be native with pandas. So that's what I mean by say extension point. Some standard that other people outside can integrate with.
So it seems like the underlying takeaway here is that the good design of interfaces and protocols is very important. And given that the scientific Python community is so broad in its needs, and that once you have one of these protocols, it's very hard to change, what should that the process of designing these interfaces or protocols look like, in your opinion?
Yeah, you definitely shouldn't trust me. I'm really bad at this. You should talk to the NumPy guys. They're very good at this, right? So I think the NEP process, they actually thought very carefully about what the NEP is NumPy enhancement proposal. They thought very carefully about this. They know this already, but I'm gonna say we need to move faster, but that process generally I think is a good process. There's a lot of community outreach, there's a lot of discussion, there's acceptance of rewrites. So we're not gonna get it right the first time, we're gonna modify it over time. So like I wanted them to make this default, but no, it has to be an environment variable to start out with. And we're sort of rolling it out over time. But talk to them. The NumPy folks are great. There's Ralph.
So you mentioned the fracturing and window of time to make a course correction. Do you have an idea on the handle of like what that time window is, and then also where do we plan?
So
where do we plan? Where do we build this plan? How do we build this plan?
Oh yeah, I have no idea. There's not like a. Lots of people today are.
Maybe it's a question to the room.
Yeah, sure. Lots of people today are like sounding alarm, like, hey, big companies are here. We should like deal with that somehow. My way of dealing with it is welcome them in with a plan, with an appropriate welcoming mat. Yeah, no idea. I mean, maybe it's too late, right? Maybe TensorFlow has already taken off. PyMC4. So PyMC3 is a good example. Theano went away. PyMC3 used to be based on Theano. Theano is end of life. They had to find a new deep learning framework. They chose TensorFlow. If you want to use PyMC4, you're in TensorFlow land. If you want to use fast AI, you're in PyTorch land. If you want to use them together, not a whole lot you can do. So maybe it's sort of a gradual thing. We're already losing a little bit, but there's lots of space.
Hi, NumPy developer. So for one, practically, how do you engage with it? Come to the sprints tomorrow, talk to us, to me, to Matty there. Also, we're not great at it. We're shipping array function in by default in the next NumPy without any high-level documentation. We're really sorry. But yes, we welcome input. We know there are like QPy developers or DAS developers. There may be, some of you may develop new arrays. Please come talk to us.
Or don't. You don't need their permission. If they're scary, you can do it on your own. They're not scary. They're great. But you could. You don't need anyone's permission. You can just do it all yourself.
Two points. One, a comment. Thank you so much for the NEP 18 protocol, pushing that forward, and the NumPy developers.
I just complained.
Thank you for complaining. It's really helpful to the community, in complaining that way at least. And another question, I think it's really cool, the DAS task graph is one really cool thing, and it was really cool running these operations on the GPU. But it seems like there's an opportunity, we have this graph that we can see what's going to happen, and then we want to run it on the GPU, but the big bottleneck for GPU computing is often sending data from the CPU to the GPU. Is there plans in the future, or is it possible to kind of prevent that happening too many times when you're executing the graph?
Yeah, so I'll put on my Nvidia Rapids hat for a moment. Why have it on the CPU? Why not just do everything on the GPU? You've got NumPy, you've got Pandas, you've got Numba, you've got deep learning frameworks. You got everything you need. So that's one answer. I'm sure there's like also technical plans that like someone actually familiar with GPUs could tell you about. I'm not that person. But more generally, we should be aware of those costs. We should explore those costs. And that's something that goes into our assessment of this new technology. So we should think about that.
All right, I think we're out of time, so let's thank the speaker one more time.